Section 3.7 Extrema. The objectives of this section are the following. We first define absolute extrema, then we define local and relative extremas, then we will find critical points of a function, and finally determine absolute extremes over a closed interval. So we begin with the first objective, which is absolute extrema. What is an absolute extreme value of a function? It is basically either an absolute maximum or an absolute minimum value. So in other terms, a function f of x has an absolute, or sometimes called global maximum, at a place where x equal to c if the y-coordinate at that location is greater than or equal to all the other y-coordinates in the interval of interest. And similarly, we will say that a function f of x has an absolute or global minimum at a place where x equal to c if the y-coordinate at that location is less than or equal to all the other y-coordinates in the interval of interest. So to illustrate this, we can see that there's a graph written here or drawn here, and it has a couple of interesting points called absolute maximums and absolute minimum. So typically speaking, what we will do is we will define the beginning of the interval as a and the end of the interval as the point where x equals b, and we are interested in finding the absolute maximas and minimas in that interval. And so as you can see from the graph, the absolute maximum is the place where the graph is the highest, meaning you have the biggest y-coordinate. So at this location where we have an absolute maximum, we would say something like f of b is greater than or equal to all the other f of x's. So it's greatest there, so that's what makes it the absolute maximum. And at this location, we have an absolute minimum. And usually, if the point is inside the interval, we will typically give it the name c. So in this case, we would say that f of c is the smallest value in that interval. And so we would write something like f of c is less than or equal to f of x. Now, does every function have to have a maximum or a minimum or an absolute maximum and minimum? And the answer is no. So for example, if you look at the function f of x equal to x squared, this function will have a minimum, but it doesn't have a maximum because the function pretty much looks like a parabola, and the lowest point is the place where x equals 0. So we will say that this is the absolute minimum, but the function will not have an absolute maximum on the interval from negative infinity to positive infinity. So let's practice finding the absolute maximum and minimum given certain functions. So this is example number 1. It says determine the absolute maximum and absolute minimum value of the function shown if they exist, because again, the function may or may not have a maximum or a minimum or an absolute one. So we begin with the y equal to x cubed minus 3x, and what's important in these problems is to always pay attention to the interval they're describing. So in this case, they're saying look at the function all over the real number line from negative infinity to positive infinity. So if I look at the graph, it seems like this function has a graph of a cubic, and we can see a couple of arrows at the beginning at the end, which means that the function continues in that pattern forever after. And so since the function keeps going down forever, right, that's how the graph is going to look. It's going to continue going down forever. It seems that we will not have an absolute minimum. So no abs min, that's my shortcuts for saying there is no absolute minimum. That's because there is not going to be a lowest point. Now you might say, wait a second, what about this location here where x equals 1? Isn't that a minimum? And the answer is yes. That is technically a minimum, but it's not a global or absolute minimum. As a matter of fact, later on in the next pages, we will say that this point where x is equal to 1 is going to be what's called a relative minimum, because in the interval around it, it is the smallest point, but overall, if I look at the whole graph altogether, then that location is not the lowest location on the whole graph, and that's why it's not considered an absolute minimum. Now, in the same way, I can see that the graph, again, on the right side, continues going up forever. So, no matter where I stop, I can continue going up. And I'm stopping here at the place where x is roughly equal to 2 or 2.1, but obviously the graph continues on forever. So therefore, again, we will say that this function does not have an absolute maximum. There is no highest point on the graph because the function keeps going up forever. And then again, you might say, wait a second, what about this location where x is equal to negative 1? Isn't that a high point? And I will say, yes, it's a high point, but it's not the highest point on the graph, because obviously any point over here on this branch of the curve will be higher than it. So we will later on in the next page say that x equal to negative 1 is in fact a relative maximum. It's not a global or absolute maximum. It is a relative maximum because in its own little area, in its own little neighborhood, the graph is highest when x is equal to -1. But overall, if I look at the full graph going from negative infinity to positive infinity, then I'll see that this point is not the highest location. That's why we will call it a relative maximum, but not an absolute maximum. Now, what's the difference between the first problem and the second problem? Well, it seems that the function is the same, but in the second problem, the interval is closed. So what do I mean by that? I mean there are brackets here, and there's a bracket there as well. That's what makes the interval closed, versus the first problem where the interval was open. That's because of those parentheses. So if I'm dealing with a closed interval, there should be hopefully at least one maximum or one minimum. Otherwise, the function is constant all the time and every point is considered the maximum and the minimum. So in this case, because the function is literally starting at -1.5 and stopping at 1.5, I am only interested in what's going on in that little world, right? I don't care about what's going on after or before, right? I don't care about those branches because my interval is closed, meaning the problem is telling me don't look at anything before -1.5 and don't look at anything after 1.5. Now, inside this region, is there a high point? Is there a low point? And the answer is definitely yes. At -1, the point there is the highest point in the whole graph. So at x equal to -1, we actually have an absolute maximum. And at the other location, where x is equal to 1, this is the lowest point there is. And at this location, the point is lowest, the graph is lowest, so there will be an absolute minimum at that location. So now be careful about the language we use to describe these places. We say that x equal to -1 has an absolute maximum. The -1 itself is not the maximum. It's that this point, it's at this x coordinate, we have a y coordinate that is the maximum. That's why I'm saying the words that x equal to -1 has an absolute maximum. It's not itself the maximum. It has a maximum. The graph has a maximum at that location. And similarly, at x equal to 1, we have a minimum. In this case, we would call it an absolute or a global minimum. Again, it's not that 1 itself is the minimum. It's that the graph has a low point when x is equal to 1. That's why we say that there's a absolute or global minimum at x equal to 1. Later on, they will ask us to describe the maximum and give its value, and to describe the minimum and give its value. And in those cases, we will have to look at the y-coordinates of these locations, and those are the values of the maximum and the minimum. So in this case, I would say that the maximum is happening when x is equal to -1, and the value of the maximum is the value 2, because that's where the graph is. That's the height of the graph at the location when x is equal to -1. And in the same way, the minimum is happening when x is equal to 1, and the minimum value is actually -2. So those are the values of the max and the minimum. They didn't ask me for this. They just said find the places where the maximum and minimum are happening. But this is something we are interested in later on in the pages that will follow. So that's why I'm mentioning it right now, so that we can prepare for those types of questions. Okay, so the last problem, we have y equal to x squared minus 3. And in this case, again, the interval is from -infinity to +infinity. And so you can see right there that there's a minimum at the location where x is equal to 0. That's the minimum because it is the lowest point on the whole graph no matter what, right? So this graph continues going up forever to the left and continues going up to the right forever. But at the location where x is equal to 0, we have a very low point. So we will say that the function has an absolute minimum, or sometimes we will say the words global minimum, and the value of the minimum is -3. So sometimes we will describe this as a point. So we will say that the function has an absolute minimum at 0, and the value is -3. So we describe it as a point with an x and a y coordinate. But there's obviously no maximum, because no matter which value you pick, if you say this is the maximum, I'm going to say, well, that's higher than it. And then you'll say, oh, there's another point higher than that. And then we can keep doing this game forever. That is the reason why the graph does not have an absolute maximum. That is why this function does not have an absolute maximum. So now we get to local relative extremas and critical points. So we'll start with the local maximum and minimum values. So what's the difference between a local maximum and a global maximum? And again, what is the difference between a local minimum and a global minimum or absolute minimum? So we say that the function has a local minimum at a point where x equal to c if the y-coordinate in that interval that is around c is the biggest y-coordinate. So basically what this means is to say that this point is a local maximum, we're basically restricting ourselves to a small area around the point, and we're saying in that little area around the point, in some open interval around the point, that point is the highest. So it may not necessarily be the highest point on the graph, because obviously any point here on this branch, since the graph continues going up to the right forever, any value is going to be higher than it. But in its own little region, in its own little neighborhood, it is the highest point, so we give it some credit and we call it a local maximum. In the same way, this point here is going to be considered a local minimum because its y-coordinate is the smallest y-coordinate in some little region around the point. Now, obviously, again, this graph continues going down forever on the left side, and every point on this side will be considered lower than the one that we're choosing. However, it doesn't matter because what we're saying is that this guy is a local minimum, meaning it's the smallest value in its own little world. So that's the difference between a local maximum and a local minimum. So if I go back to the previous page, this right here, the point where x is equal to -1, might be considered a local maximum because in its own little region, the place where x is equal to -1 has a y-coordinate that seems to be the highest. So we're taking a very small restricted view of the graph. We're not looking at the full thing. We're only looking at a little piece of the graph. And in the same way, we can say that x equal to 1, that location, will have a relative minimum because, again, in that little world, that seems to be the lowest y-coordinate, or the place where the graph is lowest. And again, we don't pay attention to what's going on here because that's not part of the world we care about. So that's the difference between a local maximum and a local minimum. Now, we also need to know what critical points are because local minimums and local maximums typically occur at the critical points. So what is a critical point of a function f? So we say that a point c of the domain of f at which f prime of c is equal to 0, or f prime of c is undefined, is a critical point of the function. So critical points of some function f of x are the places where the derivative is equal to 0, or the places where the derivative is undefined. So to know what a critical point is, you will be given a function, like this one, for example, f of x, and you will have to always find the derivative first, and then find out what makes it equal to 0 and what makes it undefined. The answer to those questions will be considered a critical point, and the places where we have critical points may or may not have a local maximum or a local minimum. So you'll see in the next few lectures that every problem will basically begin the same way. I'm going to be given some kind of function, and the first thing I'm going to do is read the question, and it's usually going to require us to find the first derivative and then asking ourselves the two questions. What makes the first derivative equal to 0? And also the second question is, what makes the derivative undefined? The answers that we get are going to be places of interest. So they may be maximas, they may be minimas, they may be what's called inflection points, and we haven't talked about that yet, but that will come up in the next few pages. But that's how every single problem is going to work. So if you're kind of confused about what to do in a problem, a good option would be for you to just find the derivative and then find out where the places where the derivative is equal to 0, or the place where the derivative is undefined. And usually you've done pretty much like 90% of the work that's required to answer whatever question you're given for the rest of this chapter. So in example number 2, we're asked to find the critical points, then look at the graph and decide whether the function has a local extreme. And by the way, when we say local extremum, we mean a local maximum or local minimum. So this is kind of including both of them. So for this first problem, I decided to type it all out for you so you can see the work. So we start off with the function f of x, which is 3x squared minus 4x minus 8. Then we find the derivative. Obviously, the derivative of 3x squared will be the 6x. The derivative of negative 4x will be negative 4. And finally, the derivative of 8 is just going to be 0, so that's why there's nothing written on the derivative side. Then answering these two questions, where is the f prime of x going to be equal to 0, or was it undefined? First of all, this is an equation of a line. 6x minus 4 has the form of a linear function, so it's never going to be undefined. So we can kind of eliminate that part of the problem instantly because there won't be solutions from that. But what makes the derivative equal to 0? That requires taking the equation 6x minus 4 and setting it equal to 0, then solving for x. And in this case, when I try to solve for x, I would have to move the 4 across, and that's what we did over here. So when you move the negative 4, it becomes positive 4. Then you will basically end up with 6x equal to 4. Then the next step will be to divide by 6 on both sides. And so x will be 4 over 6, which can be reduced to be 2/3. So that's how we're getting the critical value or the critical point. So the places where we have a critical points are the places where you will have a maximum or minimum possibly. And in this case, 2/3 is roughly around here. And if I trace to the curve, I can see that the curve is at the lowest place it can ever be. So that means at x equal to 2/3, we have what's known as a minimum. And in this case, I can obviously see that this is also known as an absolute minimum. But to be on the safe side, I'm just going to call it minimum. So when I say the word minimum alone, that allows for the opportunity to be an absolute or a relative. So don't pick the word absolute unless you're 100% sure that the number you're choosing is the lowest point on the whole graph always. So, I'm kind of cheating a little bit by saying just minimum because this allows it to be either relative or absolute, and so that's the safer option. So always go with the safer option and don't declare something as an absolute minimum unless you're 100% sure it is the minimum on the whole graph. Okay, so now let's do this together. So f of x is x cubed minus 6.5x squared minus 38x plus 240. So I would highly encourage you to pause the video right now and see if you can answer this question. Obviously, from the graph, it seems like we have a high point there. We have a low point somewhere around here. We want to know the x-coordinates of those points. So again, as a reminder, your job is to find the derivative. Then ask yourself, what makes it 0? What makes it undefined? And the numbers you get are the critical values. And for now, we will just look at the graph to decide if they're maximum or minimum. So pause the video now and see if you can answer the question. So in this question, the derivative of the function f of x will be 3x squared, and 6.5 times 2 will be 13 with an x, and then finally the 38. So this is my derivative, f prime of x, and I need to know two things. I need to know what makes it equal to 0 and what makes it undefined. So because I'm going to have to answer those questions, it's better for me to try to factor this function f of x, or in this case f prime of x, to make it easier to answer the questions that will follow up. So for this problem, I'm going to try to factor it by guess and check, or by using this big X method that we described in the past. So I want to look for two numbers that will multiply to the product of 3 and negative 38. And the numbers I need are going to be, basically, they need to be multiplied to negative 114. And since the middle number is negative 13, the numbers need to add up to negative 13. So I'm looking for two numbers that multiply to negative 114, but when you add them, you get negative 13. And I believe the numbers are going to be negative 19 and maybe 6. You can check it yourself to see that these are the correct values. And what you'll have to do is basically start off with the 3x squared minus the 13x minus the 38 and break it down as 3x squared. Then you'll have to basically break down the negative 13x, remove it, and replace it with the brand new numbers that you found. So in my problem, I'm going to put the plus 6 first, then the negative 19, then we have the negative 38 already there. And so factoring the first two, I'm going to pull out a 3x. That will give me x plus 2 as leftovers. And then from the second two terms, I'm going to factor negative 19. And when I do that, I get, again, x plus 2. So the final answer should be something like x plus 2 multiplied by 3x minus 19, right? So that's my factored version of the derivative, 3x minus 19. So I'll keep this off to the side, and that way we can kind of refer to it if we need it. But this is how you would factor the derivative f prime of x. So the questions that we needed to answer are the following two questions. What makes the derivative equal to 0? Or what makes the derivative undefined? And so for the derivative to be 0, I would need the product of x plus 2 times 3x minus 19 to be equal to 0. And since this is in fact a product, we can use the zero product property to break this down even further. For the product to be 0, it's enough for the first term to be 0 or the second term to be equal to 0. So this means that x has to be negative 2 or x has to be 19 over 3. So these are the two critical values that we get from the first half of the problem. And now what about the second half of the problem? What about, are there any numbers that would make the derivative undefined? So again, looking at my derivative, the derivative is a product of two parentheses with linear terms. So there is no way it could be undefined. So this part of the problem does not give us any extra values. I'm going to write no solution there. And so we don't need to solve it now, but it's always a good idea to check it because sometimes this will have an answer, but the first part will not have an answer, basically. So you always have to check both what makes the derivative 0 and what makes it undefined. You must answer those two questions. And so looking at the graph, I can see that the place where x is equal to negative 2, we have an absolute, actually we have a maximum. It's not an absolute max because the graph here continues going up forever. So there are places on this side of the graph where the graph will be higher than this value. So I'm just going to say that x equal to negative 2 has a maximum. And so specifically, it's a relative maximum. But I don't have to mention whether it's a relative or local maximum or an absolute maximum. Saying that we have a maximum allows for both of those options, and it's the safer choice. We know from the graph that this is a relative maximum, so if you want, you can add that word here. You can say that this is a relative maximum, but you cannot say that this is an absolute maximum. That would be false because obviously there's places on the graph that are higher than it. And looking at 19 over 3, it seems to be this point over here. 19 over 3 is a positive value, so that's the only option. It seems like we have a minimum at that location. So again, what kind of minimum is this? It's technically a relative minimum, but you don't have to really specify if you are saying just minimum. Now, if you decide to say global minimum, then you would lose points because this graph continues going down forever on the left, and every point on this side will be lower than that point, so it would not be an absolute minimum. So you can either say minimum to be safe, or if you are sure it's not the global maximum, then you can say relative minimum, and that's considered okay as well. So that's the end of that part, and now let's look again at the new function f of x, which is negative 2 with ln of x squared plus 6, x squared plus 1 plus 6, sorry. So the function that's given is negative 2 multiplied by ln of x squared plus 1, all added to 6. So what will my derivative look like? So in the previous video, we discussed how to find the derivative of ln's. In this case, ln has a negative 2 in front of it, so we're just going to ignore the negative 2 and find the derivative of ln. And we've said in the past that the derivative of a logarithm is going to be some kind of fraction where the argument x squared plus 1 gets placed in the denominator. So I'm going to be writing x squared plus 1 there, and what goes in the numerator of this fraction is just the derivative of what I wrote on the bottom, which I wrote x squared plus 1, the derivative of that is just going to be 2x. Now, this plus 6 is going to give me plus 0 in my derivative, and obviously, I'm not going to write it down because what's the point? It's just a 0. Rearranging this derivative a little bit, we can write a negative 4x on the numerator, and then just x squared plus 1 on the denominator. That's because the negative 2 technically has an invisible 1, and when you multiply fractions, you go straight across, top with top and bottom with bottom. So that would be the simplest version of my derivative. And now the question is, what makes it equal to 0, or what makes the derivative undefined? So for a function of this form to be equal to 0, since my function looks like a fraction, it's enough for the numerator to be equal to 0. So for a fraction to be 0, just take the numerator and set it equal to 0, because 0 divided by anything is going to be 0 eventually. And so solving this equation for x, right now technically the negative 4 is being multiplied by x. It would require me to divide both sides by negative 4, and 0 divided by negative 4 is really just simply 0, so I'm just going to write that down and not anything else. Now, what about the second half of this problem? What makes the function, or what makes the derivative undefined? What makes this fraction undefined? So usually what we would have to do is write down that x squared plus 1 is equal to 0, meaning the denominator of the fraction has to be 0, because any number divided by 0 will become undefined. But in this problem, saying that the denominator is equal to 0 is equivalent to saying that x squared has to be negative 1, and this does not have a real solution. In fact, it may have some imaginary numbers. If you know about imaginary numbers or complex numbers, actually the answers are going to be plus or minus I. But in this course, we don't care about imaginary numbers. We only care about real numbers. So that's the reason why I'm writing no real solution. And then I'm just going to stop here. So we only have one critical point, one critical value, and that's the place where x is equal to 0. So this is the place where x is equal to 0. Right? This is the intersection of the x and y plane, and at that location, from the graph, I see that this is a high point. It may be the highest point on the whole graph because apparently the graph keeps going down forever on the left and keeps going down forever on the right. So I can say with certainty that this is a maximum, but specifically, if I wanted to be extra smart or extra, specific, I can say that this is an absolute. But again, just to be on the safe side, I'm just going to say the word maximum. So I'm not going to use the word global maximum until I've done more work to test, and that's what we're going to do later on in the later parts of this section. We're going to check using more mathematics that this place where we have a maximum is in fact the absolute maximum or the absolute minimum or whatever. So for now, I'm just going to call it a maximum. And if you want to be safe, you can call it relative maximum, but it would not be wrong to call it global maximum in this problem because we know from further testing that there is no other point on this graph that's higher than it. So the safe way to leave this answer is to just say that at x equal to 0, we have a maximum, just like that, relative maximum or maximum. Okay, finally, we have the function f of x, which is 8x divided by 4 plus x squared. So this function f of x, it consists of a fraction with 8x on the numerator and then 4 plus x squared on the denominator. So its derivative is going to be slightly more complicated this time. We will need to use the quotient rule. So the quotient rule basically says differentiate the numerator, multiply with the denominator, then differentiate the denominator, multiply with the numerator, subtract those things, then square the denominator, and off you go, right? So I'll write the details here one final time. So this numerator is 8x. The denominator in this problem is 4 plus x squared. The derivative of the numerator is just simply 8, and the derivative of the denominator is the derivative of 4 plus x squared, which is 2x. So because I'm doing a quotient rule, I'm supposed to multiply the corners and subtract along the way, and then square the denominator, and off I go. So 8 needs to be multiplied with the 4 plus x squared, and we are supposed to subtract next because that's the quotient rule that we're using. And to multiply the other corners, we get 2x multiplied by 8x, and we're supposed to divide by the full denominator, and all of it needs to be squared. So in other terms, the f prime of x in this case, it will be 8 times 4, which is 32, plus 8 times x squared, minus 2x times 8x will be 16x squared, all divided by 4 plus x squared, everybody squared. My numerator seems to have two like terms, the 8x squared and the negative 16x squared, so I'm going to combine those two things, and I will end up with a 32 minus 8x squared, all divided by 4 plus x squared, the whole quantity squared. So this seems like a good place to stop. This is my derivative, and it's as simple as I can make it for now. So now I will start the process of finding the critical points. So how do I find the critical points? or the critical values? Well, I need to answer the two questions. What makes the derivative equal to 0? And also I need to answer the second question, which is what makes the derivative undefined? So the answer to those problems are what's known as the critical values. So again, to make the derivative equal to 0, I look at my derivative and it's a fraction. For the derivative to be 0, it's enough for the numerator of the fraction to be equal to 0. So I'm just going to write down 32 minus 8x squared equals 0. That's the numerator. And so if I want the fraction to be 0, I'll just say that the numerator needs to be equal to 0. And solving for x, I can write 32 equals 8x squared. Then I can divide both sides by 8. That will tell me that 4 is equal to x squared. And what are the values that we squared to get 4 at the end? Well, there's two of them. There's either the positive 2 or there's the value negative 2. There are two options that you square to get 4 at the end. And so let's look at the second problem real quick. When is the f prime equal to some undefined value? So what makes the f prime undefined? And to answer that question, we just grab the denominator of the fraction and we set it equal to 0. So we say that we need 4 plus x squared to be equal to 0. So for a fraction to be undefined, you need the denominator of that fraction to take on the value 0. Now, for this whole thing to be 0, we would need 4 plus x squared to be itself 0, because once you square 0, you'll get 0. And this again means that x squared needs to be equal to negative 4. And again, it happens that this has no real answers, no real solutions, because there is no real number that we square to get negative 4. But there are some imaginary numbers like 2i and negative 2i. These are imaginary values that you can square to get negative 4. But in this course, like I said, we don't care about these values, so we don't have any useful solutions from solving the second half of the problem. But we always have to check. Now, looking at my graph, what's going on at x equal to 2? At x equal to 2, it seems that we have a high point, right? The graph looks like it's the highest there, so we're going to say that we have a maximum at x equal to 2. So at x equal to 2, it seems that we have a maximum. What about the other location where x is equal to negative 2? So at x equal to negative 2, we have what seems to be a low point on the graph. Right, so this is the lowest point. So we're going to say that at x equal to negative 2, we in fact have a minimum. Now, with further testing that we're going to learn how to do later on in the next few pages, we can actually completely decide that this maximum, in fact, is what's known as a global maximum, meaning it is the highest point on the whole graph. No matter how much further you go to the left or to the right, this will always be the highest point. But for now, we haven't done enough testing to claim that. So I'm just going to stay on the safe side and call it a relative maximum or just a maximum. In the same way, the x, where x is equal to negative 2, has an absolute minimum, but we haven't done enough testing to confirm that. So to stay on the safe side, we're going to say that it's a minimum, or we can call it a relative minimum for now until we have learned how to do the extra testing and confirm that this is in fact a global maximum or a global minimum. So now, how does this change if the interval that we care about is a closed interval? So all these problems that we just finished doing had arrows over here, meaning the graph continued going forever to the left and to the right. And if you notice that none of these has an interval. So they didn't say on, negative 4 to 3, for example. They didn't put brackets or anything. I didn't see any of that notation. So those were intervals where we have an open interval, basically. So how does the work change if I have a closed interval, something like this, for instance? Well, it doesn't change a whole lot, actually. It changes only at the very end when we're deciding. So the first few steps will be the same. You'll have to find the critical values, but the way we're going to confirm whether those critical values have a maximum that is absolute or not, will require doing a little bit of extra testing, and that's what we're going to start learning in this page. So starting with example number 3, it says find the absolute maximum and absolute minimum for the function f of x equals to 3x squared minus 4x minus 8 on the interval from -1 to 3. So let's begin by first writing down the function's name. Always do this so you can always recall what function you're working with. In this case, I'm working with this function f of x. And as soon as you do that, from now on, the first step in every problem is pretty much going to be to find the derivative. So what's the derivative of 3x squared? It's going to be 6x. What's the derivative of negative 4x? It's going to be negative 4. And finally, what's the derivative of negative 8? It's just going to be 0, but I won't bother writing it down. So this will be my derivative. And the next question we will ask is, what's going to make the derivative equal to 0? And what's going to make the derivative undefined? So we need those values where the derivative is equal to 0 or the derivative is undefined. Those are the places that we call critical values. So for my derivative to be equal to 0, I'm just going to grab the whole thing, 6x minus 4, and set it all equal to 0. This means that 6x has to be equal to 4, which means x has to be just simply 2/3. So this is what we call for now a critical value or a critical number, meaning it's a place that is kind of interesting. Something is going on the graph there, and we haven't confirmed what's going on there on the graph yet, but this is an interesting place, so we need to record it, and we'll discuss further later on what to do with it. Now, what about the second half of the problem? What makes the f prime of x undefined? It does not look like my function here has anything that can make it undefined. There's no denominator to care about or to think about, or there's no radicals or anything like that. So we're going to say that this half of the problem does not have a solution. So there's no way this function 6x minus 4 can be undefined. So there's only one value that is interesting, which is 2/3. Now, because the interval is closed, sometimes we will ignore the number that we boxed in this case. Why? If the number is not between -1 and 3, then we don't care about it because it's not the interval that we are looking at. So we would basically ignore it. So for example, if I was solving this problem and I got x equal to 5 at the end, then I would say, wait a second, 5 is not between -1 and 3, so ignore it. Pretend like it never happened, basically. Now, in this case, though, the 2/3 is 0.6 roughly, and it is a number between -1 and 3, so I do have to account for it. I do have to consider it when I'm deciding the maximum and the minimum of my function. So since I don't have a graph right now, and I would like to know if the 2/3 is a maximum or minimum, how can I decide? The answer is make a table. So we're going to make a table, and we're gonna have two columns in this table. On one hand, we're going to have an x value column, and on the other hand, we're going to have the y value column. Now, the column is going to have a bunch of rows in it, and what the numbers are in these rows is going to depend on what your answers for the critical values are and the interval you began with. So I started off with the interval going from -1, so it's always a good idea to put -1 at the top row of this table, and the interval ends at 3, so it's always a good idea to put 3 at the bottom of this table. And then any critical numbers you found have to go between these numbers. So if you have 2, 3, 4 of them, make sure you put them in order from smallest to largest. That way everything looks nice and neat, and you won't make any mistakes. In my case, I only found 2/3. It was a single critical value, the 2/3, and so I'm going to place it in the middle row of my table. And now we're going to use the table method to decide who's got the biggest y-coordinate by calculating, in fact, the y-coordinate. Now, how do I calculate the y-coordinate? Remember, the function f of x that we started with is 3x squared minus 4x minus 8. This is the original function, not the derivative. That's how we decide who's the maximum or minimum. Once we have the critical points, along with the endpoints from the interval, we'll put them in the table and just plug the -1 into the x's and see what's the y-coordinate. Then we'll plug 2/3 into all the x's and see what's the y-coordinate. Then we'll do the same thing again with 3 and see what are the y-coordinates. The number that has the biggest y-coordinate is going to be the maximum. and vice versa. The one with the smallest y-coordinate will be the minimum. So let me start with -1. If x is equal to -1, what will the y-coordinate at that location be equal to? So I'm going to plug plug -1 to dx, and that will be basically 3 times -1 squared minus 4 times -1, and then minus 8. You can use your calculator to find out what the number is, and I believe the number will be -1, and I'll show you how to do this with a calculator in a few minutes, because there's a fast way to do it with the calculator. But let's do it first by hand for at least a couple of them. So what about, for example, the 3 on the bottom? So how would I find the y-coordinate of this guy? Well, I would go to my function and I would plug in 3 instead of all the x's. So it will be 3 times 3 squared minus 4 times 3 minus 8. So remember, we're replacing all the x's in the normal function of x with the critical point or the values at the endpoints of the interval. So this only works if you have a closed interval, meaning you got to have brackets for this table technique to work. If you don't have brackets, then you will not have the first row and the last row, and then you won't be able to decide just by looking at what number, the middle number, if that's the highest or the lowest. There's nothing to compare it with. So that's why we only use the table method if we're dealing with a closed interval. And by the way, 3 times 3 squared, that's going to be basically 27. 4 times 3 is 12, minus 8. The answer there should be 7. Obviously, you can do this by hand or with a calculator. And I'll show you how to do it with a calculator for the middle guy. So the middle guy is 2/3. And if I try to plug in 2/3 into my function, it's going to be a little complicated because I have to deal with fractions. I've got to square the fractions, then multiply them with some numbers, then add them with other fractions. So you know what? This is going to be super tedious. And I don't want to do that. So for now, let me give you the answer. It's going to be, roughly speaking, 9.3 negative. So a negative 9.3, roughly. And let's show you how to do this with the calculator. So I would like you to turn on your calculator, then go to the Y menu and plug in the 3x squared minus 4x minus 8. This is, again, the original function f of x that we're working with in this problem. So once you've made sure that you've put it into y1 and there's no other things on the screen, what I want you to do is to click second, your second key, then click the window key, which is in the top row of your calculator. We've done this in the past once, but maybe you didn't watch that part, or maybe you forgot, or maybe you reset your calculator recently, so you'll have to do this step only once usually. So what I'm going to do is click down a couple times until I see the independent line, INDPNT line, and I'm going to move to the place where it says ask and just hit enter. And this will basically tell the calculator, ask the user for the x values. Now in the bottom row, I'm leaving it on auto, which means the calculator will automatically give me the y coordinate. So it's asking me for the x, so I'm going to give it an x, and it automatically will return a y for me for free. Now, where do I give it the x? I click second, then I click on the graph key to open up my table. And my table should be empty, just like yours at this point. And what we do is we put the x values that we care about in this table. So the first x value that I care about is -1. Make sure you use the tiny little minus sign to indicate that the number is negative. Don't use the big minus sign. That's only used when you're subtracting two numbers on your calculator. So we need the little negative sign and then 1, and then just click enter. And you see the calculator says -1. This is the same value that we had seen previously. Okay, next we're going to type in 2 divided by 3, so the fraction 2 over 3, and then just click enter, and that's where I got my negative 9.3 earlier. So that's the second entry in my table. And to find the last entry of the table, we will just go back to the calculator and type in 3 and just hit equal. So it will say 7. Now let's say I accidentally put 4 there, and I see 24 instead. So how did I do this? How did I go back and delete it? You can always go up and down in this table by using the arrow keys. And if you put the wrong number by accident, no problem. Just type the new number on top of it and just hit enter, and it will automatically change. And you can put as many numbers as you want in this table, obviously. And if you don't want to see those extra ones that you just put in, you can just use your arrow keys to go up and then just click delete and then delete again and then delete again. And we only get the ones that we care about visible on the screen. That way it's less numbers, less confusing. Okay, so now that we finished this table, we are done building the table. We need to decide where the maximum and where the minimums are. So the table is going to help me. So I'm going to now look at the values that I got at the end. Which number is the biggest number? So I've got -1, -9.3, and 7. Which one is the biggest one? It's obviously the 7. So we will say we have a maximum at the point where x is equal to 3, and the value of the maximum is 7. So maximum at x equal to 3, and the value of the max is equal to, or in this case, y equal to 7. So the maximum is happening where x is 3, but the value of it is actually, in fact, 7. And in the same way, we're going to look at this table and decide the minimum value by asking ourselves which numbers in orange are the smallest one, right? Which number is the smallest one out of these three? So there's three values. Which one is the smallest one? I've got -1, -9.3, and 7. And obviously, this middle guy is the smallest value. So we will say that we have a minimum at the place where x is equal to 2/3. And if they ask me what's the value of the minimum, I will say the value of the minimum is roughly -9.3. And so what about this number here? It's irrelevant. It's not the max, it's not the minimum. It's just some random number that appeared to be between 7 and -9.3. So we don't actually care about what's going on at that location. Now, let's go back to the picture. So this is my calculator, and obviously I still have the 3x squared minus 4x minus 8 on my calculator in Y1. I would like to look at the graph to confirm that what we found is actually true. So what I'm going to do is go to my window and then change the minimum x to be -1 and the maximum x to be 3. Usually the y minimum is at -10 and it's usually at +10 for the y maximum. I'll leave those two unchanged, but the important thing here is to change the x minimum and x maximum to match what you have inside of your interval. Because we only care about the interval. We don't care about everything else that's happening in the universe. We just care about what's going on between -1 and 3. That's the reason why I'm changing the x minimum and x maximum to be -1 and 3. And if I click graph, I should see the picture that represents the graph of the function. So we decided that the place where x is equal to 3 has a maximum. Where is that on the screen, by the way? So I just click trace and then click 3. And the little cursor is on the far right of my screen. And you can see kind of barely there, it's blinking. But obviously, by looking at the screen, I can confirm that this is the highest place. So our math, our table is correct. The calculator is confirming what we did. We're confirming what the calculator is saying. So we're both agreeing, so it must be right. And we also said that the minimum is happening when x is 2/3. And let's trace the place where x is equal to 2/3. So I click the trace key, then click 2 divided by 3 on my keyboard, and then just hit enter. And you can see the little cursor is right there in the middle at the very, very bottom of the graph. And the y-coordinate is -9.3333 forever. So again, we can confirm that our minimum is in fact the right minimum. It is the lowest place on the graph. It's in fact the absolute minimum, and the other guy was the absolute maximum. So we're agreeing with the calculator is agreeing with us. That gives us really good confirmation that what we decided here was actually in fact true. And in fact, I can say that we have an absolute minimum at the place where x is equal to 2/3, and we have an absolute maximum at the place where x is equal to 3. You can add those words absolute, max and min, because we have conferred in multiple ways that on the interval we care about from -1 to 3, these places are the highest or the lowest. So hope that makes sense. We have one more to try out. This one has an exponential in it. So the math is going to be slightly more difficult, but the steps are basically the same as before. So I'm going to give you a minute here to pause and try to figure out the maximum and minimum of this function f of x on the interval that we are given. Again, keep in mind this is a closed interval. And if the interval is open, we will have to do something extra. That's going to be in the next section that follows this one. But for now, pause the video and see if you can get the absolute max and absolute minimum for the function f of x. So in this problem, the f of x is equal multiplied by e to the 0.5 x minus x. So we're going to ignore the 2 for a moment and just focus on the exponential. In a previous section, we said that the derivative of an exponential function is literally itself. So I'm just going to have to write down e to 0.5 again with the x in the power. But then I need to write something extra next to it. And what is the extra stuff? It's the derivative of the exponent. So the derivative of 0.5x is really 0.5, just simply like that. And the last thing I need to do is differentiate the second half of the problem. So remember, I have a negative x at the end. The derivative of negative x is going to be just simply -1. So keep that in mind at the very end. Now, before I continue any further, I'd like to multiply the 2 and the 0.5 with each other, so that way I don't have to keep writing both of those numbers anymore. So I'm just going to write down that f prime of x is equal to 1 e to the 0.5x minus 1. But this first one is irrelevant because 1 times e is just going to be e. So again, I'm just going to skip it and just write e to 0.5x minus 1 instead. This way, the function's derivative is as simple as possible. So since that's my derivative, the next two things I need to ask myself are what's the critical numbers? And we get them by saying we need f prime to be 0. Then we need f prime of x to be undefined. So those are the questions that we always have to answer. So if you don't know what to do from this point on, basically for the next like 2, 3, 4, chapters, whatever, anytime you're looking for an answer to one of these problems, it's pretty much going to require you to find the derivative and even sometimes the second derivative and do this. Find out what makes them 0, what makes them undefined. That's pretty much how it's going to be for the next few sections. So for now, my derivative is e to 0.5x minus 1, and I need it to be equal to 0. So I'm just going to grab the whole derivative and set it all equal to 0. So my derivative is e to 0.5x minus 1. And to solve for x, right now the x is in the exponent. First, I need to isolate the term that has the x in it. So I'm going to move the 1 across, so that way we have e to the 0.5x on one side and just 1 on the other side. Then we have learned in the previous section that to get x out of the power, it requires doing a natural log. And whatever you do on one side, you're supposed to do exactly the same thing on the other side. And when I do the natural log, it's always going to be written on the left side. So always write it down here on the left. Don't write 1 ln. That's kind of ridiculous. Doesn't make sense. It's ln of the 1. ln needs an argument, and the argument is basically 1. So using the special property of logs, we can take this 0.5x and write it in front. This is just an algebraic property of ln, so this is not any calculus. And so we're going to have 0.5 ln e equals to ln 1. By the way, ln of 1 is really 0. Again, we mentioned this in a previous section, but if you don't know it, you can use your calculator. And in fact, ln of e is actually equal to 1 as well. So this is saying 0.5 multiplied by 1, which is really 0.5x. So I need 0.5x to be equal to 0. What does that mean? That means x has to be itself equal to 0. So we got one useful answer, and 0 is the answer. The very first thing I do once I get it is I check. Is the number that I'm getting between the interval that's given to me? If it's not, I'm going to ignore it. And I'm going to pretend like it never happened, it never showed up. But in this case, it does fall between -2 and 3. The value 0 is a number between -2 and 3. So great, we keep it. Now, can this derivative be undefined? And the answer is no. There is no number that can make this derivative undefined because the derivative consists of an exponential function, and exponential functions have no problems evaluating any number x. If you plug any number x there in the exponent, the function does not care. It will give you a value and you're good to go. So we only have one critical value, and so now it's time to make the table. So the table of values to help us decide where's the max, where's the min. So remember, the table consists of two columns, an x column and a y column. And what do we put in the x column? We put the numbers that we care about from this problem. So first of all, we're going to put -2 because that's the beginning of the interval. We're going to put 3 because that's the end of the interval. And we're going to put 0 because that's the critical value we found. And to make sure that your table is nice and pretty, make sure you organize the numbers from smallest to biggest when you're placing them. So I'm going to place -2 first, then 0, then 3. And so those are the three values we care about. Something interesting is happening at these values, and we just need to know what exactly is happening at these locations. And remember, we need to decide by looking at the y-coordinate. And the y-coordinate is the function itself, not the derivative. So we're going to use the original function, which is 2e to the 0.5x minus x. So for the first value, when x is -2, I'm going to have to put -2 into my function, and that's going to be 2e to the 0.5 multiplied by -2, then minus another -2. So the x itself is negative, and this problem already has a minus, so make sure you put some double negatives, otherwise you will not get the right answer. And obviously this is going to be very, very difficult to do by hand, so we'll have the calculator do it next. And same way, we're going to find f of 0. In the same way, we're going to find f of 3 by putting the 0 and 3 into the function. So even though I'm not calculating anything by hand, I'm writing down the procedure just to keep reminding you that the number you're plugging in has to be plugged in into the function, not into the derivative. You get the x from the derivative, but when you plug it into the original function that was given to you in the problem. So that's super important. If you don't do that, you're going to get incorrect solutions, and then you're going to lose points on exams or quizzes or homework. Now, I don't want to have to do this by hand, and actually it's impossible for me to calculate these things by hand. So let's go ahead and turn to our calculator and see how this is done. So we still have the previous problem here on screen. So I'm going to have to reset some things so that we can get a new table going with the new numbers and the new function. So the first thing I want to do is click on the Y and just clear what's already there in y1. I'm going to type the new function in, which is 2 times e to the 0.5. So how do I get e on my keyboard? Click second, then click the ln key, which is right next to 4. So that gives you 2e, and then we will type in 0.5 and hit the x key. And then finally, close the parentheses, minus an x. So I'm using the big old minus sign over here because I'm subtracting two quantities. So this is the function. The first thing I want to do is click on graph. And obviously, right now the graph is incorrect, so I need to modify the window, right? The window used to be from -2 to 3 in our problem, but this is not the right window, so we need to change the window settings. As you can see, the window settings are still the same ones from the last problem, so you can modify them very quickly by just typing in the new interval, starts at -2 and ends at 3. And the y-min, y-max, don't mess around with them too much. We don't really care for now. So this is my graph. It looks like it's a nice little curve. It looks like it's going to have a high point on the right side of the screen, and the low point is happening somewhere in the middle. Okay, so let's confirm this. We're going to click second and then graph this time. That puts us in the table. And we have some numbers from the last problem. We don't care about them. So let's go ahead and delete everything here and start fresh. So once you've clicked delete a few times to delete all the previous entries, we're going to type in the new critical values and the new endpoints. So my new endpoints are -2. The critical value I found is 0. And the last endpoint that we had is 3. So you can see I'm getting 2.7358 and then 2 and then 5.9634. So let's transfer them to the paper. The first one was 2.7358. The second one was 2. And the last one was 5.963 and 4. So these are the y coordinates, and one of them is the biggest and one of them is the smallest, and we need to confirm which one is the biggest and call it maximum, and which one is the smallest and call it minimum. So just by looking at the numbers and comparing and contrasting which one is the biggest, which one is the smallest, I feel like I see the maximum right here. This is the highest number in the y-coordinate column. So we're going to say that we have an absolute maximum at the place where x is equal to 3. And what's the value of the max? The value of the maximum is the y-coordinate, which is roughly speaking, I'll just say 5.96 for now. And similarly, which one of these three orange numbers is the smallest one? So by looking at this guy, I'm thinking that guy is the absolute minimum. So we have an absolute minimum at the place on the function where x is equal to 0. And what's the value of the minimum? Well, it's the y-coordinate that we see in front of us, which is exactly equal to 2 in this case. So that's the end of the problem. So let's go ahead and compare what we got with the calculator again. Here is the graph of the function that we're working with. I'm going to trace the place where we have a minimum. So that's the place where x is equal to 0. And yeah, it looks like it's the lowest place on the curve. To make sure that it's super visible to you, I'm going to change something here in the window. I'm going to make my y minimum start at -1. And the y maximum, I'll leave it at 10. This should exaggerate the curvature of the curve and show you that exactly at x equal to 0, we have, in fact, a minimum. What about the place where we have a maximum? It seems like it was 3, so I'm going to trace 3. And as you can see, again, it looks like it's the highest place on the whole curve. And so the calculator is confirming what we got on our paper. We're confirming what the calculator is saying, so we are absolutely 100% sure that we've answered this problem correctly. And what about -2 itself? It's nothing. It's not the highest place and it's not the lowest place. It's just somewhere in the middle. So we don't really pay much attention to those places that are in the middle. We just care about what's going on at the most highest point and the lowest point.